Now that we've learnt about the orbit of the Earth around the Sun, we can try to now explain to you how we get the ice ages and how we can explain the ice ages based on the orbit, changes in the orbit of the Sun. And this idea that the Earth's changing orbit can influence the climate of the Earth and the ice ages was developed by Milankovitch, who lived from 1879 to 1958. He was from Serbia, and he developed, again, completely theoretically, the link between the ice ages, which come and go, as we saw, this periodic changes in the greenhouse gases and the temperature of the Earth, and periodic changes in the Earth's orbit, which then influence the amount of energy we're getting from the Sun, which also varies periodically and can influence the climate. And based on what we call the Milankovitch theory or the Milankovitch cycles, we can then explain how we can have ice sheets growing, like we can see here, which were the peak of the last ice age, covering all of the Scandinavian, northern parts of Europe and Canada, and how this can then disappear again and melt and to a situation like we have today, and then return after another, say, 100,000 years. And so his theory, which is not perfect, gives us the best explanation of how we go from ice age to interglacial, back to ice age over the last million years. So, like with Kepler, things come in threes. Milankovitch also has three parameters which he basically uses to try to explain the ice age. The first we call eccentricity. And eccentricity is how spherical or how oblique the ellipse is of the orbit of the Earth around the Sun. And Milankovitch claimed that basically the shape of our ellipse changes on a cycle of 100,000 years. Now, why does it change? Well, this is related to the pull and the push of the different planets and the Sun on the Earth. We have interaction with all the planets, all the different bodies in the solar system. They all have a force and a pull on each other. And when you put this all into a model and simulation, you get that the Earth's ellipse, the shape that it's going around the Sun, varies on a 100,000 year period. So that things change very slowly, but we go to a more oblate and more circular pattern every 100,000 years. Again, what does that mean for the climate? That when we're closer to the Sun, we're actually getting more solar radiation, we're heating up more than when we're far away from the Sun. The second parameter is the tilt of the axis. Our Earth is rotating, tilted to the plane that it's going around the Sun. At the moment, it's about 23 degrees. And Milankovitch also calculated that because, again, of the interaction and the pull of the different planets, that this tilt actually changes slightly between about 22.1 and 24.5 degrees. Now, how does this affect the climate? Well, the tilt of the planet actually results in us having summer and winter. If the tilt was vertical, if the axis of rotation was vertical, it would basically be spring or fall throughout the year. We wouldn't have summer and winter. And the steeper the tilt, the bigger the differences between summer and winter. It would be much hotter in the summer, much colder in the winter if we increase the tilt of the axis. So this tilt actually affects how much radiation from the Sun is coming to high latitudes, which can result in the melting of the ice sheets. So we'd actually like to have a more vertical axis if we want to keep the ice and the snow throughout the summer to build more and more the next winter. So when we change the angle, the obliquity, we actually change the concentration of solar energy at the surface. We can see here these two beams of light from the Sun are the same amount of energy, but when it hits the northern hemisphere, which is tilted away, we spread that same energy over a much larger area. So for every square meter, we're getting less energy, the temperatures will be lower. In the southern hemisphere, we can see that it's much more concentrated, the energy, and this is what causes the different temperatures between summer and winter. But when we change the axis, then we can actually change this distribution of the solar radiation. And again, we want to have less solar radiation during the summer months so that we can keep the snow to build the snow and the ice to lead us into an ice age. And when the tilt is decreased, then the polar region receives less sunlight in the summer and the opposite when we have a larger tilt. So if we want to build an ice age, we have to have a combination of the different parameters of the orbit, the tilt, in the right configuration so that we can have cooler temperatures in the summer. The third parameter that Milankovitch discussed is what we call the precession. The precession is actually in what direction does the axis of the Earth point at when it's at the closest point to the Sun. So it's going around in its orbit, and that normally today that axis is pointing in the same direction, but on a very long time scale of, say, 20,000 years, we see that this is changing which way it's pointing. I forgot to mention that the tilt of the axis changes on a 40,000 year periodicity. So we have one parameter which changes every 100,000 years. We have one which changes every 40,000 years. And the precession here changes approximately every 20,000 years. And this is kind of like thinking of a top, a spinning top, which is about to fall. So it's kind of precessing, and the axis of the spin is turning around. But for the Earth, it does one revolution, changing its position every 20,000 years. So how does this affect the climate? So we can see here on the top figure, we can see what the situation is today. As I mentioned, the axis is pointing in one direction today, and it turns out that we're closest to the Sun, say in our winter, if we say 21st of December, we're closest to the Sun, so we actually have kind of a modulating effect. We're close to the Sun, but in the Northern Hemisphere, we're pointing away, so it's winter. But what will happen in 10,000 years, and happened 10,000 years ago, is that the axis will be pointing in a different direction. And so what will happen is on the 21st of, when it's summer, the 21st of June, when we will be closest to the Sun, and so we'll have both closer distance and it'll be summer, which means that the Northern Hemisphere will get more intense radiation at high latitudes in 10,000 years' time as well as 10,000 years ago. And that we can see on the right, where we look at the different seasons, December, January, February, March, April, May, June, July, August, and so on the x-axis. And we can see actually the amount of radiation that we receive in the northern latitudes for the different months. In the summer, we obviously have more. June, July, August, we get the maximum. That's our summer. But we can see today the solid line is what we receive, and what we'll get in 10,000 years, and what we got 10,000 years ago is the dashed line, which shows that we get more radiation in the summer. We'll have warmer summers, which is not good for building ice sheets, but we'll also have cooler winters. So this change in the precession affects the amount of radiation and energy we get throughout the year. So we can summarize these three different parameters of a Milankovitch. The top one, again, is the change in the ellipse that is going from circular to more elliptical orbit around the Sun. The second one is the obliquity, which is around about 40,000 years, the periodicity changing the angle of the axis. And the bottom one is actually this precession, showing that at the closest point to the Sun on our orbit, which way is the axis pointing, and this varies around about 20,000 years. So if we put this all together on a plot, we can, and this is what Milankovitch did, you can go back in time, you can go forward in time, because this is all based just on theory, and we can see on the bottom, we can see the variability of the eccentricity, and again, we see that the peaks here are approximately 100,000 years apart. In the middle plot, we have the change in the angle, the obliquity, and the peaks here are separated by around about 40,000 years. And the top plot is the precession, the spinning of the top, which have a variability of around 20,000 years. But we can see that it's not constant over time. There's some periods like here, we can see where the precession kind of disappears. We don't really see a large signal. And other periods where we have a much larger impact of the precession. But we can simulate this back in time as well, forward in time, and see how this affects the climate. So here we can see now, putting these three parameters together, again, the eccentricity, and going from the present, 0, back in time 1,000,000 years. We see on the top the variation of the eccentricity related to the shape of the orbit. In the middle, we have the obliquity, the change of the angle, and in the blue, we see the precession index. And at the bottom, we can convert this to changes in radiation or insolation, the amount of solar radiation in watts per square meter that we receive at, say, 65 degrees north, where in the past we've seen that's where we have the massive growth of the ice sheets around about Scandinavia and Canada. So we want to know how the radiation at those latitudes are varying. It's less important what's happening in the tropics because we've never had ice sheets in the tropics. We want to keep those ice sheets in the high latitudes in order to move the Earth into an ice age. So we're interested mainly on the changes in the radiation occurring at high latitudes. So when we look at many different records of the climate, whether it's from pollen in the ocean, the ice cores, tree rings, isotopes in many different places, and we look at the periodicity, we find very often in the top left we can see we have periodicities in many different areas of climate research which show these typical periodicities that Milankovitch found. We see the 100,000 year peak, the 43,000 peak, 20,000 peak, and these are the key periodicities we see throughout climate research. And theoretically, Milankovitch showed that we can explain these by the changes in the orbit of the planet. And although opinions differ to some extent, we would like to have a minimum in solar radiation at the high latitudes, as I mentioned, in order for the ice sheets to grow and to expand and to cover the whole of Canada and Scandinavia. And for this, we'd need a small tilt of the Earth's axis, and we want summer to be far away from the sun at the aphelion. These will give us cooler temperatures in the summer and allow for the ice sheets to grow. Now, when we look at even longer time series, and here we see we're going back on the bottom from today, which is 5 million years or 5.5 million years, not 100,000 years or 800,000 years. We also see something interesting. In the last million years, the dominant cycle is 100,000 years. We see the ice ages and the interglacial coming and going every 100,000 years. But if we go back another million years, we see most of the variability is around 40,000 years, which appears to be closer to the change in the tilt. This is actually still an open question, and there's a lot of research of why did we get the shift from a dominant 100-year cycle to a 40,000-year cycle in the older climate. We don't have answers yet, but these two dominant cycles match up nicely with Milankovitch's theory. And so we still think that there's the long-term variability in the climate and the ice ages and interglacials can be explained in large part by changes in the orbital parameters of the Earth. So here, if we look at comparison with some climate data, so again we have on the top the precession, obliquity in the green, the eccentricity, and the solar forcing, the amount of change in radiation at 65 degrees north in the yellow. At the bottom, we can now see the differences between the glaciations, the ice ages, and the interglacial. We're starting in the present on the left-hand side. Now is today, going back, say, 1 million years. And what you can see is that these dashed vertical lines, which align with the warmest periods we've seen, the interglacial periods in the past, match fairly nicely with the peaks in blue of the eccentricity of the change in the ellipse. And we can see that the warm periods appear to be when we have higher eccentricity. The ice ages are linked more to the minimum in the eccentricity. And the other parameters that Milankovitch presented don't seem to have been that important in the last million years. If we zoom in just to the last 250,000 years, and zero again is the present, here we can see the temperature we obtained from the Vostok ice cores using those isotopes we spoke about. And the blue line is the theoretical Milankovitch cycles, which show the changes in radiation at 65 degrees north. And what we see is that sometimes we see that these peaks match fairly nicely, other times not so nicely. So generally, we can see that a lot of this variability in temperature and other parameters can be explained by the Milankovitch cycles, but not always. And so it's not a perfect theory, but it's likely the best theory we have today to explain the ice ages. And finally, we can see here also some different climate parameters which seem to match up altogether both in time but also with the Milankovitch cycles. We can see in the blue something which represents the volume of continental ice, how much ice was sitting on the land, which is in the opposite direction, the scale. So we can see during the warm periods, where the temperature is shown in the red curve, we can see that we actually had the least amount of ice on the land, but we had the most greenhouse gases, carbon dioxide, shown in the black curve. And we can look at many other parameters. One of them here in green is also showing the productivity in the oceans around Antarctica, which is also linked to these Milankovitch cycles. And so today, trying to explain the climate of the past, the fluctuations of the climate, which we see as sometimes warmer, sometimes were colder, the best theory we have to explain this is the Milankovitch cycles, changes in the Earth's orbit parameters, which impacted the amount of energy we get at high latitudes, and that sets off many other chain reactions in the oceans, in the atmosphere, in the biosphere, which will drive the climate either to a warmer climate or a colder climate. And we'll talk about all of these individual issues in more detail in the next lessons.